Chapter 4, Motion in 2 dimensions. So in chapter 2, we studied motion of a particle in 1 dimension. And as you know, in 1 dimension, there are only 2 possible directions of motion. So all the quantities with direction that we studied in chapter 2, we could use a positive and negative sign to differentiate these 2 directions. But as soon as we go beyond 1 dimension into 2 dimensions and later into 3 dimensions, we immediately find that there are infinite number of possible directions of motion. So therefore, we have to introduce vectors, and that's what we studied in chapter 3. So now we can put our knowledge of vectors to use to study motion in 2 dimensions. In fact, the difference between 2 and 3 dimensions is not that much. Once we understand how to do 2 dimensions, we can easily add a 3rd dimension. So what we're going to do is we're going to repeat our definitions for key kinematic quantities of particle kinematics in one dimension. We're going to also look at the definitions of displacement, velocity, and acceleration in 2 dimensions. See how they're different from the case in 1 dimension. So we have here the motion of a car in 2 dimensions. And I'm going to use an XY coordinate to denote the position of the car. Just like 1 dimension used X, here you use X and Y. Now, to uniquely define the position of this car, I'm going to have to use a vector which starts from the origin of the coordinate system pointing to the car. So I'm going to draw that vector now. It's like this, okay? From the origin of the coordinate system to the car. So this vector is a position vector R at a certain moment, okay? Now, a little bit of time later, the car has moved to a new position, and the new position vector, I'm going to draw it again. It's like this. Okay. Now these 2 vectors are not the same. They differ by a little bit, and I'm going to here draw the difference in these 2 displacement vectors. Position vectors. So here is a vector linking the initial and final position of this particle, of this car. Okay, this vector right here. And by the way, I'm still focused on the kinematics of particles. So I'm assuming the car can be thought of as just a point. All right, so you have R. Here is the new position R plus a little bit of change delta R, where delta R is the connection vector between the initial and the final positions of this delta R. So you see in this vector triangle, I have R and I have delta R, then the 3rd side is the sum of the 2 R plus delta R. Okay? We learned all these in chapter 3. Now, so delta R is the change in position vector from the initial to the final position, so it represents what's called a displacement vector. Okay, now if this took place during the time delta t, then the rate at which R changes would be delta R over delta t, right? So I'm going to write that down, delta R. So you start with R, and if I know that as a function of time, then the next thing I want to know is delta R over delta t. Now, as you know, this is the rate of change of the position vector. And in 1 dimension, we replace that with delta x over delta t, and that was considered to be what? The average velocity in 1 dimension. Now you have delta R to replace delta x is a vector quantity. It's a 2 or 3 dimensional displacement. So what we have here is the average velocity, which is also a vector. It points along the direction of delta R, v. Average. Okay, that's how we define it, right? Of course, that's assuming that delta t is short enough that delta R is pretty much a straight line. The car moves along the path of a straight line, so delta R pretty much coincide with the actual path. But this may not be the case if you consider the car going from here. Let me use a different color. Going from initial position to a further down final position, from here to this point, for example, Then, and clearly, as you know, the car went over a curved path. So if you were to draw a line connecting the initial point to the final point, and this line does not really coincide with the actual path, all you're getting really is the average velocity, but it doesn't really quite describe what happens, every step of the way. So if you want to know the velocity at every point, just like we did in one dimension, you're going to have to shrink delta t. Okay, so imagine you shrink delta t, so delta r gets smaller and smaller and smaller, and during such a short, extremely short time interval, the car didn't really have a chance to accelerate. So the velocity pretty much stays the same. Then what you're getting is what's called instantaneous velocity. So the idea is the same as one-dimensional case, except everything, the velocity and displacement, these are all vector quantities. So if you take limit, you take the limit of delta t going to 0, delta t going to 0 of delta r over delta t. Then what you're getting is, of course, dv dt by definition of derivative. Okay. By definition of derivative, let's go back. And so that's dv dt. I'm sorry, that's dr dt, r. That's dr dt. And that, as we know, is the velocity, is the instantaneous velocity. So this is just like the same type of definition we saw in one-dimensional motion chapter 2, besides the fact that we're dealing with vectors. Okay, so we started out from r, right? And we took a derivative. What do we get? d dt. What do we get? We get v. Now, another thing we can consider is how the velocity itself changes, and that is, I'm going to consider the rate of change of velocity, delta v over delta t. That will give me the average acceleration of the particle. Okay, and then similarly, if you take delta t to approach 0, then you go from delta t to dt, and then this average acceleration becomes instantaneous acceleration. So you got a to be defined as dv dt. Okay. dv dt, which is the second derivative of the position vector. So you take one more derivative, right? Then you will get a, just like we saw in one dimension. Of course, this process can also go backwards, and if we go backwards, we're taking integration, d dt, integral over time. Then you go from a to v back to r. Right? So far, it's really very similar to what we saw in one dimension. Now, I do want to talk about direction of these quantities, r and v and a. In one dimension, because there are only two possible directions, the velocity vector v and the acceleration vector a, they're either parallel to each other or anti-parallel to each other, right? In one dimension. And if v and a are in the same direction, so they're parallel to each other, what happens? You're moving in a direction and you've been pushed in the same direction, so you go faster, right? So you will increase the speed. On the other hand, if v points one way, but a points the opposite way, then you're going to slow down, right? So that is basically, the angle between r and v is between v and a in one dimension is either 0 degrees or 180 degrees. No third possibility. But here, once you go beyond one dimension, you see the angle between v and r can be really arbitrary. It's because when we drew the position vector r, we have to draw it relative to the starting point right here. But that starting point is, it's our choice. It has nothing to do with the motion directly. It's just where we choose to set up an observation post. So so r has an arbitrary direction depending on where we set the origin of the coordinate system. And if you look at the angle between r and v, the angle is also arbitrary. Let me draw that angle for you right here. That's the angle. Okay, this delta r is in the same direction as v. As you see, v equals delta r over delta t. Right. So this angle, can really be any possible value. between 0 and 360, this angle right here. Okay, so, but that angle is kind of, it's not very important because again, the orientation of R depends on where we choose the observation post. It is not inherent to the motion. But when we look at the relative orientation between V and A, then interesting things will happen. Okay, so let me draw, you know, the motion of a car. Let's say we have a car here. Okay, so we have this car, and it follows a certain path. It follows a certain path. Let's say it moves like this. Okay, in a zigzag path, in a curved path. I don't like this path. Let me draw something a little bit better. Say something like this. Okay, it comes in like this. Now, so at certain point, it is right here, and it's moving forward. So the direction of V is always tangential. It's always tangential to the direction of motion. It's like this. That's V. It's always like this, right? What about A though? Well, A is the rate at which this velocity vector changes, right? So I can always write A as dv dt. But how do you change a vector? You know, the velocity is a vector, right? You can change its magnitude. You can also change its direction. Or you can change both, right? Now suppose A is a vector that points in this direction. Let me draw A with a green color. So let's say A is a vector pointing this way. Oops, sorry. This is A. Now this A, the angle between A and V, I call this angle theta. This theta in our case is an acute angle, but it doesn't have to be. Let's look at what this theta really means. Of theta being acute or theta more than 90 degrees, what does that actually mean physically? Well, let's see here. I can draw a line that is parallel to the velocity. Okay? So it's tangent to the curve at that moment. So here is a line parallel to the velocity. I can also draw a line perpendicular to it. Okay, perpendicular to it, or normal to the direction of motion. Now, with that, I can break down the acceleration vector into two directions. One is along the direction of motion. The other is perpendicular to the direction of motion, right? I can always do that. I can break it down into these two components, right? So this component is a perp means perpendicular to the direction of motion. That component is a parallel because it's parallel to the direction of motion. Now, what is the physical meaning of each component? Well, A parallel is quite clear. This is the component of A that's along the direction of motion. The way I draw it, because theta is less than 90 degrees, then A parallel, the component of A along the line of the velocity is in fact in the same direction as the velocity, not anti-parallel, not backwards, but forward. So that means what? The velocity, the speed is actually increasing at this point. Okay, so A parallel is responsible for the change in speed. I can write A parallel as dv dt. This V is the magnitude, okay? You notice I didn't put an arrow here, it's the magnitude. Sometimes the magnitude doesn't change, and then this dv dt will be 0, so A parallel will be 0. That means you only have A perp left. Now, it is also possible that this angle theta is greater than 90 degrees, in which case the direction of A parallel will be opposite to the velocity, which means as the car moves forward, the acceleration is backward. So as a result, it slows down, in which case dv dt will be negative. And the negative A parallel really means that this component of the acceleration is opposite to direction of motion. Okay, so again, the physical meaning of this component is it changes the magnitude of the velocity, changes the speed. Okay, changes speed. Changes speed. Okay. In the meantime, we can look at this component. The component is perpendicular to the direction of motion, and this component of the acceleration is neither pushing the car nor pulling the car, right? I mean, if you pull the car, if you pull the car, then you go backwards, right? You push the car, you go forward, like this. This is the direction of motion of the car, right? But you're not going either forward or backward. You are right in the middle. You go like this. So you're not changing the speed, are you? Because you're not pushing it or no pulling it. But what are you doing? Any acceleration will bring the change to the velocity, right? So this is actually a component of the acceleration which changes what? The direction of motion. That's what turns the car around. Okay, so I have a perp. It has its own function. It changes it doesn't change the magnitude, but it changes the direction of motion. Okay, it changes the direction of motion. Anytime you have a change in the direction of motion, you're not moving in the same straight line, you will have that component available. Otherwise, it's not going to turn around. Okay, so this is something different. This is something we don't have in one-dimensional motion. Okay, so it is possible for a particle to stay at a constant speed, so there's no aparallel, but it still moves, it turns around, say it moves in a circle, okay, it's not in a straight line. Then is there any acceleration? Yes, because even though the speed doesn't change, or the magnitude of the velocity doesn't change, the direction of velocity still does, because it doesn't move in a straight line. So both components have their own physical meaning. All right. That has nothing to do with R from our observation post. So this is inherent to the motion. It's actually physically meaningful. So again, make sure you understand the components of the acceleration. And we'll see this perpendicular component especially important when we study what's called circular motion later. All right. Now, what do we do in order to study two-dimensional motion? Do we have a special technique to study two-dimensional motion? Or is it similar to one-dimensional motion? Well, it's got its two-dimensional motion certainly has its own features that we don't see in one-dimensional motion. However, as we learned in chapter 3, when you deal with a 2 or 3-dimensional vector, all you have to do really is to break it down to its components, right? X component, Y component, or maybe if it's 3-dimensional, add a Z component. And X, Y, Z, these are just scalars. These are not vectors, right? Each component is just a number, which is a scalar. And that same technique can be used to study two-dimensional motion, especially when the acceleration of the two-dimensional motion is constant or uniformly accelerated two-dimensional motion. Because what we can do is to break down the motion into X and Y directions. And along each direction, you look at the X component, look at how it moves along the X direction and how it moves along the Y direction, you'll find that it's just a one-dimensional motion, something we already learned how to do in chapter 2. And then all we have to do later is to combine the effect of the motion in one direction, X direction, in the other direction, the Y direction. Then we can get the whole picture. Okay. Again, this is particularly useful if the acceleration is uniform, because we can always point one of the XY axis along the acceleration, and the other axis will have zero acceleration. Okay. Now, before we settle down to study the acceleration of a special case of uniformly accelerated motion in 2 dimensions, we have to look at some general pictures first. So as we saw here in the beginning, you can go from R to V to A by differentiation, and we wrote the formulas here. But let's write down the formula to go from A back to V and then back to R by integration. So you have you have v, you start with dv equals a dt, right? Or because a equals dv dt. Then we can integrate over both sides. From initial moment of 0 to the current time t, and the velocity went from v initial to the current value v, and then when you finish the integral on the left-hand side, it's just v minus v initial, okay? And you can move that v initial to the other side, and then plus the integral of a dt. Now, I don't know what this integral leads me to, because I don't know what a is as a function of time. If you tell me what that is, I can finish the integral for you. And similarly, you can go from v to r. You start with dr equals v dt, right? And you can integrate both sides. Here is from the initial time of 0 to the current time, and here from r initial to the current location r. And then you do the same thing as you did before. R equals r naught plus what? This integral. Okay, this integral. So this is a general mechanism, but we usually don't really study complicated cases where a and v can change, you know, in a fancy way. Rather, we're going to focus, just like what we saw in one-dimensional motion, we're going to focus on a special case of uniformly accelerated two-dimensional motion. In fact, there are two special cases we study in this chapter for two-dimensional motion. One is uniformly accelerated two-dimensional motion, especially an important case of that, which is what's called projectile motion. Okay. The other is a case where the acceleration is not quite uniform, yet somehow the motion is still rather simple and extremely important, and that is circular motion, especially uniform circular motion. Okay. Uniform circular motion is not a motion with uniform acceleration. The acceleration actually changes, believe it or not. But still, it's got its own unique features, which makes it easier to study than just an arbitrarily non-uniform acceleration. Plus, it's extremely important, you know, because we see that all the time in real life. So we're going to study that also as a special case. Okay. Now, before we get on to circular motion, let's first focus on uniformly accelerated two-dimensional motion, and let's see how we can do that. And again, the idea is to break it down into two directions, x and y, and we can put the acceleration along one of these two directions to make our job easier. And then we just combine the information in the x direction and the y direction together to get the whole picture. So for uniformly accelerated motion, I can actually finish the integrals over for a and v over time. So let me write that down now. If a is a constant, okay, then what can we say about v? We can then finish this integral. It's v naught plus what? Well, integral of a dt, a is a constant, take that out, it's at. Okay? Even though v naught and a, they can have totally different directions, you know. So the final velocity, initial velocity may not be along the same direction at all. But what about r? Well, r equals to r naught plus, I can finish this integral by plugging in the expression of v here, v naught plus at, and then integrate over time. That's a very simple integration to do. The first term is this v naught times t, right? The next term, a is a constant. Where I take that a out of the integration, what's left is t dt integral. Isn't that 1/2 at squared? 1/2 at squared. Right? So that's r. So you get these two useful expressions, which we have seen before in one-dimensional case, right? I mean, one-dimensional case, we have v equals v naught plus at, except there's no vector signs. And we have x equals x naught plus v naught t plus 1/2 at squared. Very similar, except now we have r and v and a all with caps. They're all vector quantities. So they can all have totally different directions. Now, again, we can break down the motion into x, y directions, so we can utilize our knowledge of one-dimensional motion separately in the x direction and in the y direction. For example, if you start with v equals v naught plus at, this vector equation, you can write down the x component of that. Okay, so let's see, break down. Into components. This is the key here, because then we can borrow our knowledge of one-dimensional motion. So let's how we do that for the first equation, v equals v naught plus at. V itself equals vxi plus vyj. That's what we learned in chapter 3, right? Same thing with v naught, and a, I can write it down as axi plus ayj, right? And then this equation that we saw for v breaks down into two components. Vx equals to v naught x plus axt. And then I have vy equals v naught y plus ayt, right? And we know how to deal with each of these. We have seen them in chapter 2. And especially if the acceleration really is a constant, because it is, otherwise we cannot even do that, right? These equations are not even valid, ax and ay. We can set the x direction to be, for example, along the direction of total acceleration. So ax is just a, whereas ay simply becomes 0. So it's easier for us, right? So that is, the best strategy when it comes to studying uniform accelerated two-dimensional motion. That is to put the acceleration along one of the axes, either x or y. We see that in the application later. Okay, now physically, the idea of breaking down motion into x, y direction, I can draw a picture for you to understand what is the physical meaning of that. Let's say we have this ant that crawls along this blue curve. Okay, it's a two-dimensional motion. How do we study this fancy curve that goes up and down? It's not very easy to study by itself. So what we're going to do is we are going to, let's say, cast a beam of light. Okay, well, let's say we cast a beam of light down like this. And this beam of light will then drop a shadow of this ant onto the x-axis. Okay, so this ant now has a shadow. So along the x direction, it's here. In the meantime, we can also cast a beam of light towards the y-axis, and then the ant also drops a shadow on the y-axis. All right. So it does this. Here's the shadow of the ant on the y-axis. Now, if we focus only on this dot, that is the shadow on the x-axis, this dot will start from here, right? And it's going to go like this, keep on going, keep on going. It's not necessarily uniform, but at least it's one-dimensional. We can use whatever knowledge we have about one-dimensional motion to study how this dot moves. And in the meantime, this other dot also moves along the on the y-axis, right? This other dot moves on the y-axis, so it starts from here, right? And it goes up, and then it goes down along the y direction, right? Keep on going up and down, and then we can study how that shadow moves. So we're going to focus on each shadow one at a time because it's just a one-dimensional motion. And then we combine the information of both x and y. We can pinpoint exactly where this ant is two-dimensionally, in which direction it moves, and so on. So that's the idea, okay? And the same idea can be even used for three-dimensional motion. So for three-dimensional motion, let's say we have this skyscraper. We use that as a reference for z-axis, okay? To establish a z-axis. Let's say we have this b, and this b flies in a three-dimensional path. Can be in a fancy path. What I can do is, first of all, let me cast a shadow of this B onto the skyscraper. I draw a z-axis on the skyscraper. So I cast a shadow this way. So it's going to drop a shadow of the B on the skyscraper right here on the z-axis. And so as the thing flies like this, the shadow on the z-axis does this. It can go up and down, back and forth. But that's the information about how high it is, right? with whether it moves up or moves down. In the meantime, I drop a shadow of this bead onto the ground, which is the XY plane. Okay, so here's how I cast the shadow, and then you know, the shadow goes all the way down to the ground. And this is where the XY plane is. So here's the shadow right here. So look at the shadow on the ground, it does this, you know. The path is like this. So we've now reduced this three-dimensional motion to a one-dimensional motion plus a two-dimensional motion. And then we can further reduce it to two extra one-dimensional motions, one in the X direction, one in the Y direction, by breaking down the shadow on the XY plane to the shadow here along the X-axis and other shadow here on the Y-axis. So basically I look at all these three shadows, 1, 2, and 3, then we can figure out where the B is at every point. Okay, I find X, I find Y, I find Z, using our knowledge of one-dimensional motion separately, and then we combine information together, we can study, we get a whole picture of how this beam moves in 3 dimensions. Okay, so that's the whole idea of studying two or three-dimensional motion. So in the next lecture, we're going to focus on uniformly accelerated two-dimensional motion, especially a special case called projectile motion. And that is the motion under the influence of gravity, but unlike free fall, this time we're going to project this thing out at a certain initial velocity, not entirely vertical. So it's going to leave this vertical line, it's going to project a two-dimensional path called a projectile motion. And we can see how we can use our knowledge of one-dimensional motion in the X direction and one-dimensional motion in the Y direction to study the two-dimensional projectile motion to get information we're looking for.